In previous videos, we've looked at the quadratic formula for finding the roots of an equation, so our negative b plus or minus square root of b squared minus 4ac over 2a. What we're going to look at is a specific part of that formula that allows us to determine the types of roots of a quadratic, but take that a bit further and look at coefficients and solving parts of equation, finding variables for that. We're going to look specifically at the discriminant. We're going to look at that part of the formula. So quick refresher of what that is first, then we're going to look at how we can apply that in examples. So remember, we have our quadratic set in the form ax squared plus bx plus c equals 0. We need it to be like this and to be equal to 0 for us to solve it and find the roots. Now, using the part of the quadratic formula called the discriminant, which is this part here, the b squared minus 4ac, what we're able to do is determine the types of roots that the equation has. So when we calculate b squared minus 4ac, there's three possible scenarios that could occur. First scenario is the value of b squared minus 4ac is bigger than 0. What that means is we're taking the square root of a positive value, and because we're adding and subtracting to get two different answers, we're going to end up with two real roots for the equation. Second scenario is when b squared minus 4ac equals 0. What this means is there's no square root part for us to add and subtract from our value, so we're going to end up with the same value twice. So we're going to end up with one repeated root. And if we end up with b squared minus 4ac is less than 0, we're taking the square root of a negative number. Now this could result in an imaginary number, but we're not going to worry about that at a higher level, so we're just going to say this gives me no real roots of the equation. So based on these, you can actually kind of get the idea as to how the graph looks. For two real roots, if you think about it again, it cuts the axis twice. For one repeated root, it touches the axis and no more, so it would look something like that or like that. And for no real roots, it wouldn't touch the x-axis at all, so it'd be floating in midair above or below the axis like this. That's how they would look. Now, we're able to determine the types of roots that a function has, but we're also able to take this a step further. If I was to give you a function with a missing coefficient, or a coefficient which was a letter, you can then take the condition of the types of roots and determine what that coefficient should be. So I'm going to show you a few examples of this and how we'd apply that. So let's imagine I want you to find the value of p, which gives one repeated root when I give you the equation px squared plus 3p minus 4x plus 4 equals 0. Now, as soon as you see something like that which talks about the types of roots, instantly think your b squared minus 4ac. But you have to think of the condition. Now I want a one repeated root, so that means I'm looking for when b squared minus 4ac equals 0. From this, I have to take my a, b and c, plug them into here and solve the equation. So looking at this, I know that a is going to equal p. This part here, the 3p minus 4, that's going to be my b. And my plus 4 here, that's going to be my c. So I've got all three parts I need now for my discriminant. It's now a case of just plugging them in. So if I plug it all in, I get 3p take away 4 squared take away 4 times p, which is my a, times c, which is 4. And I want that equal to 0. So then it's just a case of multiplying this all out, simplifying it and solving it. So 3p minus 4 squared, that gives me 9p squared, take away 24p plus 16, take away, well this bit here, 4 times p times 4 is minus 16p. And I know that that equals 0. We simplify all this together and we get 9p squared take away 40p plus 16 equals 0. And then it's just a case of solving this and finding the value for p which I'm after. So factorise the whole thing and I get one bracket with 9p minus 4, the other bracket with p minus 4, and I know that's equal to 0, and I get my two solutions from that. So I get one solution when 9p minus 4 equals 0, or another when p minus 4 equals 0. This one here gives me p equals 4 over 9, and this one here gives me p equals 4. Now, if it had given me other conditions, so for example, if it said find the integer value of p which gives one repeated root, I would be able to select just a singular value. But it's not given me any more conditions, so I can't. At this point I have to leave it, and I've got two possible values for p where I'd get a repeated root. Let's take a second scenario now. So the question here is what range of values of b gives two real roots? Now we know we're after a range of values because if we think back to the discriminant, for two real roots we want b squared minus 4ac this time bigger than 0. So we want this condition met. So we have to do this, but we'll find some sort of a range, rather than just 1 or 2, as we did in the previous example, specific values. But we approach it the same. We figure out the values of A, B, and C, substitute them in, and take it from there. So A, we know is going to equal 1. B, well, that's just equal to the B, which is the coefficient of x. And C is equal to 4, and then it's just plugging it in. So plugging this all in, I get B squared, take with 4 times 1 times 4, and that has to be bigger than 0. So I've got B squared minus 16 is bigger than 0. So if I factorise that, I get B minus 4, B plus 4 is bigger than 0. So now I've got to figure out the times when this is met. So I've got to figure out when B meets this here. Well, these roots here are B equals 4 and B equals negative 4. So I know if I pick either of these two values, I'm going to be multiplying by 0. So essentially my curve is going to look either like that, and I've got negative 4 and 4, or it's going to look like that, and I've got negative 4 and 4 here. I need to figure out which of these conditions it is. So I need to figure out which of these values gives me that. Now remember, if it's negative between negative 4 and 4, it would be this sort of case here, and that would mean I'd get no real roots. If it was positive, it would be this case, and I'd get my 2 real roots within this range. I need to figure out which parts of the graph that is. So if I look at just less than 4, so let's imagine that B is less than negative 4. So let's say it's negative 5. That would give me negative 5 minus 5, so that would give me a negative. Negative 5 plus 4, that would be another negative, and that would be positive. So that's bigger than 0. So I know if B is less than negative 4, I get a positive answer. So my B squared minus 4AC is less than is bigger than 0. That's one condition. So I know that part of it's going to be B less than negative 4. Let's imagine I now take a value in between these two. So imagine I take a value somewhere between negative 4 and 4 for P. What's going to happen then? So let's imagine 2, 1, negative 3, something like that. Any value between here. This one here is going to be a negative bracket. This one here is going to be a positive bracket. It doesn't matter if my value is negative, because the size of the value is somewhere between 4 and 0, this 4 here will always dominate, so this will always be positive, and this one will always be negative, so I'm always going to get an answer that's less than 0. So it can't lie within this set of values here. If I then pick a value for B which is bigger than 4, so let's say 5, 6, 10, a million, what that means is this is going to be positive, and this is going to be positive, so I'm going to end up with a positive number times a positive number, which I'm going to say, and I know, is bigger than 0. So that's the one I want there as well. So I know I've got a range of values for B. What I'm then able to say is therefore B less than negative 4 or B bigger than 4 gives me 2 real roots. Any value in those areas gives me satisfactory values for my roots. It gives me 2 answers. So that's what we need to figure out. Okay, working with these sorts of ones can be a little bit more complex, but think of it in terms of this. Look at it where the changing of the guard is, if you like, where it changes from these at the roots. So another example for us then, this time we're going to look at no real roots. So what range of values gives no real roots for it when I've got kx squared plus 2x minus 6 equals 0. Now remember, for no real roots, b squared minus 4ac has to be less than 0. So it's got to be a negative value for that. So that's what I'm looking for when I solve this equation. So it's the same set of steps to begin with. I still need to figure out my A, my B and my C, and I then take it from there. So in this case, A is equal to K, B is equal to 2, and C is equal to negative 6, and I then plug it into my equation. So I get 2 squared, take away 4 times K times negative 6 has to be less than 0. Work all these values out, and I get 4 take away, well, 4 6s are 24, but it's 4 times negative 6. Minus minus gives you a plus, so it's 4 plus 24k is less than 0. I can then jiggle this about just like I would when I'm solving a nice simple inequality. 24k is less than negative 4, so k is less than negative 4 over 24, which is negative 1 over 6. So what I'm then able to say is if k is less than negative 1 over 6, I get no roots. So I get no real roots. They'll all be imaginary and involve complex numbers. We're able to do it for any of those. We have to just remember the condition on our roots. If we're after 2 real roots, it's going to be bigger than 0. If we're after 1 repeated root, it's equal to 0. And if we're after no real roots, it's got to be less than 0. We have to figure that out.